Okay, welcome to our video finally on non-dimensionalization. Now, before we get into it, let me just motivate our study of non-dimensionalization a little bit. The big idea is that we're going to take an equation that relates quantities, either independent variables, dependent variables, like the function that we want to solve for in a differential equation, but also the constants that show up. And we're going to make changes of variables, except for maybe it's not really a change of variables because we also want to do it on constants, which we wouldn't want to call constants. So we're going to rewrite this thing in terms of new variables and constants that are dimensionless, meaning that say, at the beginning, and we'll take a look at an example here, but maybe in the original equation I had stuff that was in terms of time, stuff that was in terms of length, acceleration, or volume, or whatever, but my new variables and constants are all going to be combined with the old ones in a way that all of these dimensions cancel out. And now there's a couple of important reasons why this is useful in the study of differential equations. Probably the more important reason, at least when you're doing numerical analysis, is that it levels the playing field for these quantities. Meaning that maybe I had built my equation with a really large length scale and a really small time scale. It's fine to do that, maybe that was important for the problem, but especially if I'm trying to find numerical approximations of solutions for this, I can run into some really crazy rounding errors just because, on the one hand I have really big lengths and I have really small times, and I'm multiplying them together or doing whatever in the equation, and it can cause some problems for approximation. Another reason, which is a little bit more important to us in this class, is that it can drastically simplify our differential equation and make it much easier to work with. Of course, once you've made this change and non-dimensionalized, there's not really like a physical meaning for each of the quantities themselves, but once we've solved our differential equation, we can go back and undo these we can undo the non-dimensionalization, which really just amounts to scaling each of our variables. So let's get to it. Here I have our first example. I'm going to do two examples. One is an ODE and one is a PDE. This is our first example. It's an ODE that describes the force acting on some sort of thing that is moving away from the Earth's surface. Okay, so maybe a spaceship, maybe a baseball if you were to throw it up, doesn't matter. Actually, spaceship is probably better because for things that don't go up very high, you can just kind of assume that the force is constant. We always say, oh, the constant acceleration due to gravity, which is 9.8 meters per second squared. The problem with that is that that's only the acceleration at the Earth's surface. Once you move further away, of course, the force of gravity affects you, and it changes by the distance of the object to the center of the Earth squared. That's what we have right here. So let me go through really quick and tell you what each of these things are. So m is the mass of the object. H is height of the object. T is time. g is the acceleration due to gravity at the Earth's surface, the 9.8 meters per second squared. So I'll just call that acceleration due to gravity. At the surface. And r is the radius of the Earth. So that when we add h plus r, that is the distance of between the Earth and the object. And finally, we have v, which is an initial velocity. Okay. Now, for the purposes of non-dimensionalization, I don't really care what each thing actually is at this point. I just kind of care what type of quantity it's describing. So m, I'm just going to write as mass. H, instead of height, I'm going to call it length. T is time. G is acceleration, but I'm going to call that, this is length over time squared. R is just length. And V is velocity, which is length over time. Of course, I can just, we have this m sitting in the front of both sides of the equation, so I can just divide everything by m. I don't really need to worry about mass, and everything else is just in terms of length and time. Now, when I non-dimensionalize, I always start with independent variables. And we only have one independent variable here. That is time. And I want to non-dimensionalize it. Now, so, hold on. Yeah, this is fine. Okay, so I have time right here, and I need to scale t, make a new variable. Sorry, that's why I was confused. I want a new variable tau, which is going to be some scaling of t that cancels out with the units of time. Now, the only place where I can get a single time, because I do have gravity that has time squared, the only place I can get a single time is v. So I know I can cancel out the time in t by multiplying by v, but the problem with that is now I also have a length in there, and so I want to divide by something that involves length, which is either r or h. Because I just want this to be a constant scaling of r, and h is not a constant, it's just a dependent variable, I am going to divide this by r. So now you'll notice that if you were to do some dimensional analysis of this guy, we would have L over T, that's the dimensions of V, where L is length and T is time, multiply by the dimension of little t, which is just time, and then divide that by L. So everything here, all of the dimensions cancel each other out. Okay? So that means that tau is now a dimensionless independent variable. And all we had to do is scale it by v over r. Our dependent variable that is h over here. And we can just divide that by r and call that big H. And that's just, this is length over length. So that is also dimensionless. Okay, I think that's gonna do it. So let's see what happens when we substitute, or when we make a change of variables from h and t to big H and tau. Let's see what our initial value problem becomes. So first of all, I want to figure out what, let's see. So if I take big H, I'm going to take the derivative of H with respect to tau and see what happens. Okay, so of course I'm going to get a 1 over r times dh d tau, but I can rewrite dh d tau as dh dt times dt d tau, thanks to the chain rule. And that means that, let's see, looking at my definition of tau, t equals r over v times tau, so dt d tau is r over v. Yeah. And right? Yeah. Dt d tau is r over v, and that means that we get 1 over v dh dt. Okay, and the second derivative ends up being, let's see, it's going to be an r over v squared dh dt. So this is the second derivative. Okay, and so when we make the change of variables from little h to big H, the left-hand side here is going to become v squared over r times d squared big H over dt squared, tau, d tau squared. Okay, and then this equals on the other side. I know that g still has dimensions, but so does v squared over r. So we'll take care of that in a second, and I'll write this right here. Now, when we make the change here, little h equals r big H, so we get this. And of course you can factor out an r from that and divide the top and the bottom by r squared, and it just becomes this. That means that, let's see, I could multiply r, both sides by r over v squared. G r over v squared, and then just call this some constant. I'm going to call it a, and write it up here. Okay, And that's beautiful. Of course, when little h is 0, so is big H. So the first initial condition remains the same. But when we look at dh d tau, that is 1 over v dh dt. And so h prime of 0 equals v over v, which just equals 1. Okay, and here at the end I just want to check really quick to make sure that I did this right. One sign of that will be that A is dimensionless, because this whole side is dimensionless. The bottom down here is dimensionless, so A should also be dimensionless. And we said that A was, it was just G times R over V squared. And if we look at the dimensions of this, G is acceleration, so that's L over T squared. R is L, and V is velocity, so that's L over T. And you can see that those do indeed cancel out. So A is dimensionless. This entire equation is dimensionless. And look, it's just simpler, right? I mean, before we had G's and R's running around. Now we only have an A as a constant in this problem, and we only have it in one spot as opposed to having like an R squared up here and an R down there, and plus our initial condition became this really nice 1. So then I could go and solve this differential equation, find a solution for big H, make the change of variables back to convert it to little h in terms of t, and then I'll have a solution for my original problem. Okay, so it's great. All right, let's do another example. Okay, example number 2. All right, so here we have Fisher's equation. This is the equation that we use to talk about population growth, but we've added this spatial diffusion term, although x is only in one spatial dimension. Okay, and let's start by identifying each of these terms in here. Our independent variables are x and t. X is length, and t is time. We have this dependent variable u, which is, since we're talking about population growth, u is the size of the population at a given time t and at a point in space x. We also have, remember we talked about this in class a little bit, something called the carrying capacity. And remember, this is like an equilibrium population size. At least if you were to take this term out. And so the carrying capacity is because it describes a population size, a specific population size. The dimension of this is also population, just like u. We also have these constants d and r. D is a diffusion constant, and r is a growth rate. If you have experience with this type of dimensional analysis, you probably already know what dimensions these are, but if this is your first time seeing it, it might be hard to think of what the dimension of a diffusion constant would have to be. So we're going to perform a little bit of dimensional analysis here. I know that the left-hand side, because it's a derivative of u with respect to t, I know that this is population over time. Okay? And that's really valuable knowledge to me now, because I know that the total dimension of the right-hand side also needs to be population over time. And since there's two terms that we're adding together, in order to add two terms together, they have to have the same total dimension. And so each of these has to be population over time as well. So let's start with this one. Uxx, that I know that that is population over length squared. Each time I take a derivative with respect to x, I'm getting an inverse length dimension. So the second derivative is p over L squared. And because this term has to come out to p over t, that means that d must be L squared over t. So length squared over time is the dimension of the diffusion constant. Similarly, if I look at this term, let's see, I know that u is population, and this term in the parentheses here is dimensionless, because I have u over k, which are both they both have dimension p. So that means that my growth rate r has to have a dimension of inverse time. Okay? And this will help me find the change of variables that I want. So let's start with independent variables. I'm going to do t first. My new dimensionless time I'm going to call tau, and I want to multiply t by some constant that will cancel out its time dimension, and of course r will do that quite nicely. So tau is going to equal r times t. Next I have x. This one's a little bit more difficult. I know that I have a length here. The only other place that I have a length in these terms is in diffusion, but it's a length squared. So I'm going to have to divide by square root of d. But of course that also gives me, I have now that total dimension is square root of t, because, let's see, this would be L divided by square root of L squared over t. So that comes out to square root of t overall. And so I need to do something to get rid of that. I'm going to also multiply by a square root of r, because that will give me square root of 1 over t on top here. I can write this a little bit nicer like this. Oh, and my new dimensionless variable, the book likes to use psi, so we'll use that. All right, so there we go. There's my independent variables. Dependent variables. We have u, and we have a really nice scaling here. Just divide u by k. I'll call the new variable big U, and so this is little u over k. Okay, so now I'm ready to make a change of variables here. Well, let's see, before I do that, I would like to figure out the derivatives of u, of big U, with respect to my dimensionless independent variables. So for example, u tau, this is going to equal 1 over k times du d tau, but from the chain rule I can just write du d tau as du dt times dt d tau. Since t equals tau over r, dt d tau is just 1 over r. And that means I get big U tau equals 1 over rk du dt. Okay, now let's find the first derivative with respect to xi. Similarly, this is 1 over k times du dx times dx dc. And dx dc is square root of d over r. If we take another derivative with respect to xi, we're still going to have this 1 over k in front. And taking another derivative of u with respect to xi is just going to bring out another square root of d over r. So this just becomes times d over r. All right, so now making this change of variables is going to be pretty straightforward. I have so du dt equals rk big U with respect to tau. So we get this, and we're going to have d times uxx, which is what, rk over d times big U xi. And then we have plus r times, since big U equals u over k, little u equals big U times k. So we get this times 1 minus u. Of course, these d's are going to cancel out, and you'll notice that every term has an rk, so we'll divide that from everything to get u tau equals u xi plus u times 1 minus u. And it just doesn't get any better than that. We have a dimensionless differential equation. There's no constants running around other than 1, but we can handle that. So that's really beautiful compared to the original differential equation. Of course, as a reminder, big U doesn't really have it doesn't have any dimensions, right? So that's not actually a population. It's just a function that we're solving for. But it's proportional to an actual population. If you were to just multiply big U times k, then you get an actual population. And so once you solve for big U, you can just scale all your variables back to get an actual population little u. And so that turns out really nice. Now, in the first non-dimensionalization problem in the homework, which is number 5 of section 1.3, is a little bit difficult. When it talks about a porous media equation, it's talking about equation 1.3.21, which is at the top of page 32 in the book. And there's a lot of crazy quantities running around in this, and you'll kind of have to read through page 31 to understand what everything is. Make sure to do dimensional analysis to figure out dimensions of things like the volumetric flow rate, V. Oh, never mind, that doesn't show up here anymore. Yeah, so it's going to be a little bit harder than the example right here, but you can do it, and I'm happy to help. All right, see you later.